Hello everyone, this is Akifa Tasneem welcoming all of you in Advanced Communication Networks group presentation. We are group 14 and the paper we are going to present is named as Refining Network Intents for Self-Driving Network. Let's go through the keywords from the title one by one. The word self-driving means for a machine operating without the guidance of a human which is automated. The vision of a self-driving network describes the eventual combination of telemetry, workflow automation, DevOps, and machine learning to create an infrastructure that is responsive, adaptive, and ultimately predictive. Now, what is network intent? Network intent or intent-based networking is an emerging technology concept that aims to apply a deeper level of intelligence and intended state to replace the manual processes of configuring networks and reacting to network issues. In the introduction of the paper, the author introduced with intent-based networking, that is IBN, which allows operators to specify high-level policies that dictate how the network should behave. For example, defining goals related to quality of service, security, and performance, without worrying about the low-level details that are necessary to program the network to achieve these goals. Unfortunately, most of the existing research proposals for IBN fail to exploit the knowledge and feedback of the network operator. Highly complex and sometimes conflicting policies in network devices may cause network intents to derail from the desired behavior of the operator. The key insight of their process is an intermediate representation that resembles natural language that is suitable to collect feedback from the operator but is structured enough to facilitate precise translations. The prototype interacts with a network operator using natural language and translates the operator input to the intermediate representation before translating to SDN rules. To give an overview of this paper, the author defined self-driving network, an autonomous network that can predict changes and adapt the user's behavior. They also mentioned about the failure of the research proposals on IBN. Hence, this paper proposes a process that consists of 3 stages: making an intelligent chatbot, translate the extracted entities into a high-level structured network definition program, to compile extracted intent program into a network policy. In summary, the author mentioned key contributions of these papers are novel intent refinement process for intelligent extraction of intents from natural language that uses feedbacks from network operators to improve learning. NILE, a high-level, comprehensive intent definition language that resembles the English language to reduce the need for operators to learn a new policy language for each different type of network. Experimental results that show significant improvements on translation accuracy with the feedback of the operator. Refinement process. A network operator should be able to specify network policies without worrying how they would be achieved. Hence, using natural language would be even better solution. This section presents the 3 stages of the refinement process: entities extraction, intent translation, and intent deployment. This figure shows an overview of the refinement process with the 3 stages and the steps involved in translating intents described in natural language to network configurations. The operator provides feedback via chatbot interface in step 6, and steps 2 to 6 are repeated until the operator confirms the correct translations of the intents. Entities extraction. In the first step in the intent refinement process is to extract the actions and targets of network behavior expressed in natural language by operator. To build the entities extractor, Dialogflow was being used because of the key advantage, which is the ability to deploy the chatbot across multiple platforms, including Google Assistant, Amazon's Alexa, Slack's, and Facebook Messenger. Intent translation. After all the necessary entities has been extracted, a webhook was configured from the chatbot to intent translator to receive all the extracted entities. These entities are fed to a previously trained sequence-to-sequence learning model. A neural sequence-to-sequence learning model consists of two recurrent neural network RNN with long short-term memory LSTM hidden units, an encoder and a decoder. In this model, the RNN encoder processes the sequence of words and generates a thought vector. The RNN decoder receives the thought vector as input and generates a sequence of words in the destination language, in this case Nile programming language. This figure shows an example of the encoding and decoding process. Intent deployment. Finally, having a structured intent program verified by the operator in intent deployer can compile and deploy into a destination network. In this stage, assertions were made to verify any conflicts between the extracted intent and the network configuration and warn the operator through the chatbot interface. Then, Nile programs were translated into configuration commands using Sonata NFV. Finally, Nile Intent Definition Language. This is a language that is simple yet comprehensive abstraction layer between lower-level policies and the natural language used by operators and home users. Translating natural language intent directly to network rules decreases portability and reusability, since each possible destination network has specific features and configuration requirements. To bridge this gap, Nile language has proposed as an intermediate intent representation that is close to natural language. With this language, they build a powerful yet simple intents. Now, the implementation part will be described by my team member, Rifat.
In this section, we will look at how the authors proceeded with their implementation. The authors used different GitHub projects for each stage of the refinement process, and they also made parts of their project available for others. They did this because they wanted it to be more convenient for people who wants to download and reuse stages of their project separately. So authors started by implementing the entities extractor as a Dialogflow chat interface and deployed it for testing in the Google Assistant platform. These chat interfaces consisted of entities which are key featured to be parsed from natural languages and language intents. So the language intents represent the possible user interaction that a chatbot creator provides for the machine learning training, and so that Dialogflow can generalize and learn how to extract the necessary entities for future interactions. And authors also uploaded the exported implementation of chat interface from Dialogflow as JSON to GitHub, so if anyone is interested in their project, they can have a look. The authors also implemented the intent translator as Python RESTful API service that is called by the Dialogflow chat interface right after it extracts the entities. And these services can interact with the chatbot interface to ask for additional information if necessary. And beside these interactions, the API provides a sequence-to-sequence model developed during Keras that authors use to train the model. And authors also trained and computed the weights of the model with an automatically generated dataset of input entries containing examples of anonymized entities and the correspondent Nile program, which was also anonymized. And they conducted this project using different sized dataset, and after generating null intents and confirming it with user feedback, authors retrained the model by adding the intent to the training dataset. To assess the feasibility of intent refinement process, the authors evaluated two main aspects. So the first being the accuracy achieved with different sizes of training datasets, aiming to end the optimal ratio between dataset size and the prediction accuracy. And the second point being the impact of the operator feedback on the accuracy of predictions over time to determine if it improves accuracy. So authors ran the experiments on a server with 8 Intel Core i7 processor running at 3.4 gigahertz and 16 GB of RAM. The servers generated the datasets automatically with random sets of entities and null intent pairs, combining a different number of middle boxes, endpoints, traffic matching rules, time, and QoS requirements in each intent. And all training iterations were done with 70 epochs and having batch size of 64 and a validation split of 20%. The experiments were evaluated in 5 different sizes. So they had 100, 500, 1000, 2000, and 500 entries for each training datasets. To assess the first aspect, authors first trained the transition model and measured for each prediction in the testing dataset the correlation coefficient squared between the intent predicted by the model and the expected output. So for this case, the closer to the R-squared value, the more accurate the transition model is. From the graph, we can see, I'm not sure if the graph is clear enough, but on the left-hand side, the graph is R-squared against the dataset. So the more datasets you have, it provides better results. And on the right, it's the training time against the dataset. So naturally, the larger the dataset is, it requires more time to train. Next, authors evaluate the impact of the operator feedback in the accuracy of the prediction with the same dataset. So to simulate the process, authors first loaded the neural network weights for the trained model. And they used 30 different test cases of entities and expected null intents to simulate requests from an operator. So we can see from the graph, on the left hand side is the R-squared value, and at the bottom we have the number of feedbacks, and different color represents different data sizes. So having more feedback improves the results, but that's not always the case, because at some cases the value was good with less entries, but overall dataset with more entries showed close to perfect results. To illustrate how the end-to-end deployment process of intents work, authors represented a test case that concerns service chaining using Sonata NFV. The scenario consists of a network with two open vSwitches connecting an iPerf client that sends 100 megabits of UDP traffic to its server and a web client that generates HTTP requests to the web server. So we have a better image in the next slide. We will look into that in a while. So after starting both clients, authors tested the user intent. So the intent being, please add a firewall and an IDS from iPerf client to server. Intent translator converts the input entities into null intent. So the image on the right, that's the null intent. So the user intent being converted into null intent. And intent deployer compiles translated null program into the Sonata NFV command. So the one at the bottom, that's the Sonata NFV commands. So this is the better version of the previous slide. We can see the two switches, so one being connected to the servers and the other being connected to the clients. So when the user says, please add a firewall and an IDS from iPerf client to server, we can see the firewall and IDS being added to the network after the intent gets translated to Nile program and then gets compiled to Sonata NFV. To conclude and evaluate, let's quickly look at the things we learned from the paper. So the authors introduced novel intent refinement process and the Nile program, so which is a high-level intent definition language. And we looked at the refinement process, which leverages user-friendly chat interfaces and sequence-to-sequence learning model. We also saw Nile acting as an abstraction layer for a lower-level configuration and policy languages. And we also saw the overall project yielding a result of having correlation coefficient squared of 0.99. So that's a pretty good result. So the closer to 1 the result, the better it is. And the feedbacks from operators improved the overall test accuracy, especially for smaller number of data sets. Thank you.